Welcome to this fluid mechanics course. My name is Daniel Ofe and I am a mechanical engineering lecturer. Before we begin, I would like to apologize for my voice. Unfortunately, this is all I've got and I've tried to do something about it, but it always sounds or it ends up sounding a little sleepy. So if I sound like I'm about to sleep, please don't worry. I promise the course itself will be much more exciting than my voice sounds. Now, my goal is to make fluid mechanics simple, practical, and even enjoyable. Because when I was a student, I wasn't always happy with the way the course was taught. Many concepts felt much more complicated than they needed to be, and I know many students still feel the same way today. So that's one of the main reasons why I am creating this course, to reach students who find fluid mechanics difficult and to show that it doesn't have to be intimidating at all. Now we'll go through the course step by step using clear explanations, and we'll actually solve plenty of worked examples. Some of these examples will be theoretical, while others will be based on real engineering applications. So you will not only understand the concepts, but you also see how they are used in practice. So whether you are taking fluid mechanics for the first time or you are just here for a refresher, I'm very confident you learn something valuable. And by the end of this course, I hope you not only understand fluid mechanics, but you also appreciate the ideas behind it. Let me introduce you to my assistant. Now, anytime you see that liquid being on fire, then it means there is a question that I might answer. So I would look for ways to answer questions that might be on your mind as we treat the topics. So let's start with fluid mechanics. So mechanics itself is a broad area of engineering which talks about three things. So we have the mechanics of rigid bodies, we have the mechanics of bodies that deform, and then we have our own special topic, that is fluid mechanics. So fluid mechanics is the category of mechanics which deals with the behavior of fluids, whether they are at rest or they are moving. So how do we differentiate between the mechanics of solids and the mechanics of fluids? So from the little knowledge that we know, we can say that anything that flows is a fluid. And if we are talking about things that flow, then we are definitely talking about gases and liquids. So as an engineer, everything depends. Here in this case, we can say that solids flow all right, but it depends on the temperature. Because if I put a metal on fire, it will definitely begin to flow at a certain point in time. Also, we can talk about things like sand in a container. So sand in a container can be poured just like water in a bottle. But the sand particles, however, are solid particles. When we pick one grain of sand, we realize that is actually a solid. So we are going to even use that concept to explain why fluids flow. So let's establish the difference between solids and fluids. So from our basic knowledge in physics, we can recall that due to the force of attraction between solid particles, the molecules are very close together because each particle is pulling the other one with a very high force of attraction. And that is why we can say solids are highly packed. Liquid particles are also packed just like solids. The only difference between liquids and solids is that the force of attraction in solids is significantly higher than that of liquids. So that makes the particles in liquids drift away from each other slightly when there is any form of deformation. Gas particles don't have any form of attraction between them. They are always moving at high speeds, and the only time they meet is when they collide to either release energy or absorb some form of energy. So let's look at the differences under these topics. The first one is mobility of molecules. So particles in solids are actually immobile. It's very difficult for one particle to say it is moving because it is held in place by the attraction of all the particles that are around it. So it becomes very difficult for one particle to move. For the case of liquids, the particles can actually move. This is because the force of attraction between the molecules are not very strong. So one particle can drift once there is enough energy to move it from that point. For gases, they are always moving about because there is nothing to even hold them in place. Then let's look at the next difference, which is the density of solids compared to other fluids. So solids generally have a very high density, and liquids follow, and gases have very, very low densities. Density is basically the mass over volume. That is the number of particles that are present in a particular volume. So for the same volume of solid, liquid, and gas, we'll have more particles packed in the solid compared to gas. So an example is steel has a very high density, which is around 7,700 kilogram per meter cube. And we know water has just 1,000. So look at the difference, 7,007 and 1,000. And then air has a density of 1.2. That is a very huge difference. Then we can also talk about the molecular spacing between the particles. So for gases, the spacing is very high and the spacing reduces such that solids have the least amount of spacing between the particles. Then the next difference between them will be their viscosities. Solids don't flow. So in the first place, we don't even talk about viscosity when it comes to solids. However, for liquids, viscosity is a measure of how they flow. So different liquids show different viscosity because they flow differently. And for gases, the viscosity is very low because they move with little to no resistance. And the last thing we talk about is their compressibility. So solids are highly incompressible because of the nature of their packaging. Liquids are compressible, but the energy needed to compress them is very, very high. You know, we've said the packaging of liquids is just like solids. The only difference is the force of attraction. So liquids are also sometimes considered incompressible. For gases, however, because of the spacing between the molecules, we can push them together, and we can have things like compressors that can actually compress gases and push them into our car tires. And to define the compressibility of fluids, we use what we call the bulk modulus of elasticity. So we'll see that when we start looking at the properties of fluids in another video. Now that we've seen the difference between fluids and solids, let's look at the definition of a fluid. So a fluid is generally defined as any substance that deforms continuously when acted upon by any amount of shear force or shear stress. So coming back to the force of attraction between the particles, we are expecting that for the case of solids, when you apply any force to the solid at any point, the whole object is supposed to move together. However, for a liquid, the case is different, as we have established that the force of attraction between the particles is very low. When you apply any tangential force to any fluid particle, it is expected that the forces cannot hold them together as they would in a solid. So that is what causes the deformation. Each particle or the number of particles that you have shift over each other, and they cannot resist that shear force or that tangential force. So once you keep on applying the force, we expect that the liquid will continue to deform. And this is what causes some liquids to flow easier than others. So for instance, you can have honey and water. One flows easier than the other. And all of this is just as a result of the weak molecular forces between the particles. So we can say that for honey, the particles have bonds that are stronger than that of water. And this is a property of fluids that we call viscosity. Now let's look at the branches of fluid mechanics. There are three main branches that we can talk about. We have hydrodynamics, gas dynamics, and aerodynamics. So hydrodynamics is just one branch of fluid mechanics that deals with the motion of liquids, especially water. That is why it is termed hydrodynamics. So the hydro there is just for water. We can apply hydrodynamics in water supply systems, hydroelectric power, and then pipeline flow. Then gas dynamics deals with the motion of compressible gases when they flow under high speed. At these kinds of speeds, we expect that the densities will change. So because there are spaces between the particles, we are expecting the densities to change as they move very fast. And once there is some form of allowance, then the particles can come closer together. We apply gas dynamics in nozzle designs where we have to push fluids through certain spaces at high speeds. Then we also have an application in rocket propulsion where high-speed gases have to come from the exhaust of rockets to push the rocket up into space. Then the last one is aerodynamics, which deals with the motion of air and how certain objects can move through air. So this is applied in how we design things that generally have to go through air. So things that have to face the resistance of air in how we use them. For instance, we have cars, trains, we have bridges, and even buildings that have to constantly face the effects of air moving around them. Then we can talk about the three subcategories of fluid mechanics, that is statics, kinematics, and fluid dynamics. Fluid statics basically deals with fluids at rest. Then we have fluid kinematics, which talks about how fluids move. Then dynamics talks about why fluids even flow in the first place. Now let's talk about the units of measurement that we might need in fluid mechanics. So basically we've seen some of these things before. We have the SI system, which is very easy to work with. Then the British system, which you have to get used to before you can even use comfortably. So as engineers, we need to study both systems and know how to convert even between the two systems. So for instance, in the SI system, we measure length in meters and we measure length in feet or inches under the British system. For mass, SI says we should measure in kilogram and the British system measures in the pound mass or the slag. Some of these units are just derived from their formula. For instance, area is just the length times the breadth of a rectangle. So we have the meter times the meter, which gives us the square meter. And if the SI system is saying square meter, then we can go to the British and write the square feet. Some of these units can be derived from the formulas of the quantities. Then we have what we call dimensional homogeneity, which says that we shouldn't add or subtract two things when their units are not the same, because 2 plus 2 is not always equal to 4. You can have 2 apples plus 2 apples, which is equal to 4, but 2 apples plus 2 tables, we don't know how to put that together. So always make sure you have the same units before you can add. Sometimes we will have units in kilo and other units in the normal unit system. For instance, we can have kilopascal and pascal. We should be very careful in how we approach some of these units. Then we also need to know how to convert from one unit to the other, because sometimes you would have in the same question or in the same situation where there are different units of the same quantity. We can't work with the two units within the same situation. So we must convert one unit to the other. Knowing how to do that makes you a more efficient engineer. And I will always tell my students that doing small things in big ways actually helps you to get there faster and safer than chewing the answers in your head. For instance, I have a baby method or a long method of converting units from one form to another. So let's look at that briefly. Then the last thing we are going to talk about in this session is the boundaries and systems. So what is a system? We say a system is the specific quantity of matter or the region in space where we are interested in studying. So we select a certain space for analysis, and that becomes our system. There are two main systems that we can talk of. We have the open system and the closed system. So those are the two. The open system allows both mass and energy into the system. So such a system is like an open classroom where human beings can enter, and then heat or energy in the form of heat can also go in and go out of the classroom. Then the closed system only allows energy to enter or leave the system. So such a system is when you have a room that is closed. So the room is closed to human beings, but we cannot prevent heat from entering the system. That is our room. Then we have a special type of closed system called the isolated system. So the isolated system does not allow heat or energy to enter the system. So this system has high insulation so that even energy cannot cross the boundary of the system. On that note, let's look at boundaries. Basically, a boundary separates the system from its surrounding. So the surrounding is anything outside the system that we are not interested in. And we need to create a division between the system and its surrounding. So some of these boundaries can be real, they can be imaginary, they can be movable, or they can even be stationary. An example of the real boundary is the walls in which we find ourselves. So if my room is my system, then the walls become my boundary, and that is something that I can see and touch. So it is a real boundary. For an imaginary boundary, sometimes when we deal with large systems where we cannot actually create a real boundary that we can see, then we just create an imaginary boundary where we can study that space and then generalize it to the whole fluid. For instance, when I have a liquid flowing through a pipe, then I cannot create a real boundary inside the pipe. However, I can create an imaginary space where I'll study the fluids that pass through that space, and then I can generalize it and then say the fluid that I have behaves in this way. So that is the imaginary boundary. Then we can have the stationary boundary and the movable boundary. Some boundaries do not stay at one place. They can move from time to time, and we have to factor that in any analysis that we make when studying such systems. So this ends the introductory part to our course. In our next chapter, we'll be looking at the properties of fluids and some properties that we would need to continue the other chapters.